Welcome to this in-depth course on configuring the Innodb engine in Mysql. This course covers everything you need to know about the Innodb storage engine, starting with setting up Linux and Mysql, followed by a detailed dive into Innodb architecture and features. We'll explore critical areas such as buffer pool configuration, log buffers, and flush methods. You'll learn how to manage table spaces, optimize transaction logs, and test advanced features like the Innodb dedicated server. With hands-on experience at every step, you'll gain practical skills to confidently configure and optimize Mysql with Innodb. Let's get started. In this video, we'll show you how to install Ubuntu on your Windows machine using WSL2. You'll be able to run Linux commands seamlessly alongside Windows. First, let's enable WSL2 on Windows. Go to search and type turn Windows features on or off. Expand this. Next, we will select Windows Subsystem for Linux and Virtual Machine Platform. We will click OK. Windows is prompting us to restart our device, so we will restart now. After the restart is done, we will set WSL to use version 2 by default. Then we will copy paste this command into the terminal. The operation was completed successfully. We can see our current distros by using the WSL-list command. There are no installed distributions, and as I mentioned, we can install them by visiting the Microsoft Store. Let us go. Once the Microsoft Store is open, we can search Ubuntu. We can download Ubuntu from here. Click Get. Once that is finished, we will click Open. So we got this error, distribution failed with this error. This is not a difficult error to fix. First, we will type WSL-update. Then we will install Ubuntu with the command WSL-install distro Ubuntu. We will wait some moments for this to install. We are prompted to give it a new Unix username. I will give it the name techm. Next, we are prompted to give a password. Please remember these credentials, guys. Now we are logged in as user techm and we can now use Ubuntu on Windows. We can check the version of Ubuntu with this command. We can check the Linux kernel version with this command. We can update package lists with this command. This is why you should remember your credentials in order to use the sudo command. So that's it. You've successfully installed Ubuntu on Windows using WSL2. Now you can run Linux commands right from your Windows machine. If you found this helpful, make sure to like and subscribe, and I will see you in the next video. Thank you and have a great day. Hi guys, today I'm going to show you a step-by-step guide to installing MySQL Community Edition on Linux. I'm going to be hosting the Linux operating system on an EC2 instance from AWS. Let's get started. First, I'll open EC2. Actually, before you get started, you need to have a Windows subsystem for Linux working on your Windows device, or you need to be on a Mac. That's how I'm going to be proceeding with this. If you don't have that, I have a previous video showing you how to set that up. It's pretty simple. All you just search up is if you don't turn Windows features on or off. And then you just click the two boxes. You click Windows Subsystem for Linux and Virtual Machine Platform. Then it will prompt you to restart the device, and then that'll be all set up if you don't have it set up. First, I'll create a new instance. I will make a EC2 instance. It'll all be in the free tier. I'll call it demo. I'll browse more AMIs. I'm going to go with the Amazon Linux 2 AMI. This is the image that'll be installed onto our EC2 instance. It will be imitating a CentOS Red Hat Enterprise Linux operating system. For the key pair, just for demonstration, I might as well just make a new one. I'll call it whatever I want. I'll just call it key 5. I'm going to SSH into this EC2 instance, so now it's in my downloads folder. Make sure you allow SSH traffic from anywhere. Otherwise, you won't be able to SSH into the VM. I might as well put 30 gigabytes. It stays in the free tier. Also, guys, keep in mind, I'm using T2 Micro, which is free tier eligible, so I won't be charged for this. That is all. We will launch the instance. The instance is running. Now I will open up a new terminal. First, I will enter the Ubuntu system on Windows. So that's just WSL-D. Next, I downloaded that key. Key 5. I'm going to copy it into my Ubuntu file system so that I can SSH into the VM. I've already made a folder on this in this Ubuntu file system called key. So I'm going to copy it into this folder. So we just use the cp command. Then it's the source folder. So in order to access the Windows file system from our Ubuntu file system, we always have to use the mount because it's mounted onto the system. Mount C drive, users, techm, downloads, and then key5.pem. And we're going to, the destination will be in the home key directory. I got to do sudo. Put the password. And there is key 5 right there. Next, let's go to the instructions so that we can SSH into my machine. Not instant state, we gotta connect. So we got to do this change mode, because if the permissions are too open on your key, it's not considered secure. So we got to do sudo in front of this. Okay, that's done. And then we SSH into it. Not you. Now we're going to SSH into it. So again, put sudo in front of it. Yes. And there we go. We are now in EC2. We are logged in as EC2 user at this IP. We can see more details about our VM if we run this cat, if we read more into this folder using the cat command. So as you can see, ID is like CentOS, Red Hat Enterprise, Linux, Fedora. So that's the OS we're going to be installing MySQL Community onto. I will provide all the commands for this so that it's super easy for you to follow along. First, we will download the MySQLite repository package using this command. Next, we will install the MySQL repository locally. Sudo yum local install MySQL community release. Yes. It is complete. Next, we will import the public key for MySQL8. Next, we will install the MySQL server. Yes. Yes. Oh, we get this failing package because I made a mistake when I imported the public key. Here I put 2022. You want it to be 2023. There. I'll make sure that this is correct in the commands that I will give to you so that you don't get this error. So once again, we'll have to install MySQL server. But if you didn't get that error, you don't need to. Yes. As you can see, it's taking longer because it's actually able to install all the packages. And we got the complete message this time, no message of failures. Next, we will enable the MySQL service to auto restart on reboot. Systemctl enable MySQL daemon service. Next, we will start the MySQL service. We can check the status of the MySQL service. There you have it. It is running. We can get the process ID of the MySQL service. There it is, 3C3635. We can see if we are listening for connections on port 3306. You shouldn't, if you don't know, port 3306 is the port MySQL uses. We are listening for connections. We can list all of the files being used by the MySQL user. All of these files are being used right now by MySQL. So we can clearly see it is running. And that concludes our step-by-step guide to installing MySQL 8 Community Edition on Linux. Thank you for watching. If you found this helpful, please like and subscribe, and I will see you in the next video. Bye. Now that we have MySQL installed, let's go ahead and secure our MySQL installation. First, we must access the root password. We can find it in this directory in this file. So this is the root password. It needs to get reset to whatever we decide. There is a script there is an executable that we get called MySQL secure installation. We can use the which command to determine the path of this script. We will find it here. This second command provides information about the script's file type. We can see that it is a 64-bit executable file designed for GNU/Linux systems, which uses shared libraries and is optimized for performance by being stripped of unnecessary information. Next, we can run the MySQL secure installation script. Let's go ahead and we can run it with this sudo in front of it. We are being prompted to enter the current password for the root user. Copy it, paste it, enter. We are being prompted now to reset the password, set a new password. Make sure your password is complex enough, having special characters being long enough, and having numbers in it so that you don't run into any problems. Let us confirm it. We are being prompted if we want to change the password. Yes. 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 Do we want to remove anonymous users? Yes. Do we want to disallow remote root login? Yes. So this means that I can't log in as the root user from another device, which is better for security. Do you want to remove the test database? Say yes. Do you want to reload privilege tables? Yes. Now we are all done. Let's go ahead and log into MySQL to verify if we can access it. So we will do MySQL. Host is going to be localhost because we're logged into the device having the MySQL installation. User is root, and we can just put password like this and we will be prompted for it. And there we go. We are in. Let's go ahead and do a quick select statement to retrieve and display the hostname, server ID, and version of the MySQL server and confirm that it's running correctly. So we will do hostname, server underscore ID, version. This SQL command retrieves and displays the hostname, server ID, and version of the MySQL server, confirming that it is running correctly. There's our hostname, server ID, and version. And there you have it. That is the tutorial on securing your MySQL installation. If you found this video helpful, please like and subscribe for more tutorials, and I will see you in the next video. Bye. Let's dive deeper into the Innodb storage engine. We've touched on some basics, but now let's explore what makes Innodb such a valuable component in MySQL. Understanding the purpose and functionality of a storage engine like Innodb is crucial since it's responsible for safely storing the final state of your data on disk. Knowing the inner workings of this engine helps us appreciate how it balances reliability and performance. One of the key strengths of Innodb is that it's built for general purpose use. This versatility makes it equally suitable for OLTP and OLAP applications. In other words, Innodb's design offers the ideal combination of data reliability and performance. By default, MySQL 8 uses Innodb as its storage engine. It fully supports data manipulation language, DML, operations, and it's based on the ACID model, which ensures data integrity through atomicity, consistency, isolation, and durability. The engine handles all types of transactions with options to commit, rollback, and even recover data in the event of a crash. For concurrent access, Innodb employs row-level locking, which helps prevent conflicts when multiple users access the same data. Another key feature of Innodb is the way it stores the data. Each Innodb table is organized with a primary key index, also known as a clustered index, which structures the data on disk according to the primary key. This organization optimizes retrieval speed by minimizing data fragmentation. In addition to efficient data organization, Innodb also enforces referential integrity through foreign key constraints, maintaining the relationships between tables. Innodb offers other powerful features like data compression, caching for both tables and indexes, and data encryption for security. It also includes support for full-text search indexes, replication, and data storage up to 64 terabytes. Plus, it offers fine-grained row-level locking. This is just an overview of what Innodb brings to the table. Thank you for watching, and I'll see you in the next part. Let's dive into the architecture of the Innodb storage engine, picking up where we left off. To keep this simple, there are two factors to remember when it comes to optimizing a storage engine's performance: memory and disk. The more memory you allocate, the more responsive the database will be. Similarly, faster disk storage will make a big difference in how quickly your database performs. In short, boost memory and speed up your hard drive, and you'll see real gains. However, keep in mind two rules that go hand in hand with this. First, even if you allocate tons of memory and use a fast disk, a poorly designed database structure will slow you down. If tables lack primary keys or indexes, or you're running queries without filters, you won't see the performance benefits from these resources. The second rule is that even with a perfectly designed application, a shortage of memory or slow disk speeds will still impact performance. Now let's go over two main structural components of Innodb: the in-memory structure and the on-disk structure. In memory, we have the buffer pool. This is where table and index data is cached, reducing the need to access the disk for frequently requested information. We have the change buffer. This temporarily stores changes to secondary indexes, making updates more efficient. We have the adaptive hash index. Think of this as a high-speed, in-memory index that provides quick access to frequently accessed data. We have the log buffer. This temporarily holds changes before they're saved to the log files on disk. On the disk side, we have the system table space. This holds metadata and manages data across the databases. We have the double write buffer, a data integrity feature specific to Innodb that ensures data is correctly written to disk. There's the undo table space. These manage undo logs, which help maintain data integrity during transactions. There are redo logs. This keeps track of changes that have not yet been saved to the main data files, aiding in crash recovery. There is the file per table tablespace. Each table has its own data file, allowing for better data management. There is the general tablespace, which is used for storing multiple tables if needed. And finally, there is the temporary tablespace, which is specifically used for temporary tables and operations. These components of InnoDB's architecture work together to manage data effectively. As we move forward, we'll go into each of these in more detail, but for now, take a moment to visualize these elements in InnoDB, and we will continue soon. Thank you for watching, and I will see you in the next part. Let's go into more depth about the InnoDB buffer pool. In our previous lesson, we introduced this pool as a dedicated memory area that the storage engine uses to cache table and index data as it is accessed. Imagine we have a Mysql installed on a server with a portion of main memory allocated specifically for the InnoDB buffer pool. This is part of the in-memory structure managed by InnoDB to improve database efficiency. Now here's a best practice. Mysql should ideally be on a dedicated physical hardware, with no other applications sharing memory. Aim to allocate around 80% of the memory to Mysql, leaving about 20% for the operating system. The buffer pool has a key variable, InnoDB buffer pool size. This value defines the portion of memory the storage engine uses, specifically the InnoDB buffer pool. For example, if you have 16 gigabytes of RAM and assign 8 to 10 gigabytes to Mysql, you'd set that amount in InnoDB buffer pool size. Alongside InnoDB buffer pool size, there are two related settings. The InnoDB buffer pool instances. This defines the number of buffer pool instances. For larger databases, dividing the buffer pool into smaller instances can improve performance. Then there's the InnoDB buffer pool chunk size. Each chunk is typically 128 megabytes by default. For smaller servers, a single buffer pool instance is sufficient, but larger setups benefit from multiple instances, enhancing concurrency. The formula for this is the InnoDB buffer pool size is equal to the InnoDB buffer pool chunk size times the InnoDB buffer pool instances. Let's say we have a small server with 2 gigabytes of RAM. In this case, you might set the InnoDB buffer pool size to 128 MB, as it aligns with the default chunk size multiplied by one instance. To view the current buffer pool configuration, you can run the command show engine InnoDB status. This command provides details on transactions, row operations, and buffer pool allocations. It's a great way to check the memory allocated to InnoDB and ensure your configuration is optimized. Make sure that you understand this concept well, as it is foundational for understanding how Mysql uses memory. Thank you for watching, and I will see you in the next part. In this part, I'll show you how to check and adjust the InnoDB buffer pool size in Mysql. To begin, let's look at how much memory is currently allocated to the InnoDB buffer pool, which is part of the storage engine's memory area. This space caches data from tables and indexes, allowing for faster access. First, let's log into Mysql and enter the show InnoDB status command, and this command provides detailed information about the InnoDB storage engine, including a section on the buffer pool memory allocation. So here we can see the buffer pool size in terms of pages, and to convert it to megabytes, we would just divide by 1024, giving you the size in MB. Here we can see the buffer pool size. This command provides detailed information about the InnoDB storage engine, including a section on buffer pool memory allocation. We can also check the configure buffer pool settings by using the show global variables like InnoDB buffer pool. This displays values like the InnoDB buffer pool size, which represents the current buffer pool size in bytes. By default, this may be set to 128 MB depending on the server configuration. We can also see that buffer pool size is just buffer pool chunk size multiplied by buffer pool instances. Let's say we want to increase the buffer pool size to 256 MB. Let's go ahead and look at how to do this. We will exit. Next, we will do sudo vim and go into the my.cnf. This is where the CNF files are kept in MySQL. The MySQL configuration file is kept. Let's say we want to increase the buffer pool size to 256 MB. To do this, we would just go and open the MySQL configuration file like this using the sudo vim. Next, we hit I to enter insert mode, and we're going to add the following line to set the buffer pool size. So we're going to hit enter, and Innodb buffer pool size is equal to 256 M. Now we hit escape, shift : right quit. Okay, so we will stop the MySQL d.service, and basically just restart the whole thing so that our changes can be applied. Then we'll start it. Now we can verify the new configuration. We'll just enter MySQL, show engine, or show global variables like Innodb buffer pool, and we can see it has doubled since the last time. And we can show the Innodb status, and we can see the buffer pool size is double. And if you convert this, it'll be 256 MB. Increasing the buffer pool size allows MySQL to cache more table and index data in memory, improving access speeds and overall database performance. Thank you for watching, and I will see you in the next part. In this lesson, we're diving into the Innodb log buffer, a crucial component for managing transactions efficiently in MySQL's Innodb storage engine. This is part of the memory structure MySQL uses to handle and store data efficiently. The log buffer is a memory area that temporarily holds changes to data before they are saved to disk in redo log files. This buffer helps transactions proceed without needing to commit to disk right away, which is much faster since memory access speeds are greater than disk access speeds. Using the log buffer, MySQL can group multiple transactions before writing them to the disk, reducing disk input, output, operations, and improving performance. The Innodb log buffer size variable controls the log buffer size. MySQL 8 sets this to 16 MB by default, but you may want to adjust this depending on your workload. A larger buffer is particularly beneficial when dealing with large transactions or many frequent transactions. With a bigger buffer, MySQL can handle more in-memory transactions before needing to write to disk, saving on disk operations and speeding things up. If the log buffer can't accommodate the transactions, MySQL must stop and flush the data to disk before proceeding. This delay is called a log wait. You can monitor these log waits by checking the Innodb log waits status variable. Each time this value increases, it indicates a situation where MySQL had to wait for the buffer to flush. If this happens frequently, consider either increasing the Innodb log buffer size or breaking large transactions into smaller parts to reduce the buffer demand. For your assignment, examine the Innodb log buffer's current size and use the Innodb log waits status variable to determine if the buffer size is sufficient. This may suggest a need for a larger buffer size to support your workload. With this understanding of log buffers, you're one step closer to optimizing MySQL's performance. In the next lesson, we'll go over how to apply these settings in practice and monitor the results. See you in the next lesson. In this lesson, let's dive into MySQL to look at the current configuration for InnoDB's log buffer size and understand how it impacts transaction handling. So first I'll log into my instance. I'll go into MySQL. First, we need to verify the existing buffer size for the InnoDB logs. To do this, let's check the global variable that holds this information. We will run show global variables like InnoDB log buffer size. The value here is displayed in bytes. If you convert this, it is equal to 16 MB, which is the default setting for MySQL. Having this value set to 16 MB typically provides enough space for most environments to hold logs temporarily before they are flushed to disk. However, we'll talk about when you might consider changing it. Next, let's check if there are any log waits. Log waits indicate when the buffer becomes too full and transactions have to pause briefly to make space. To see if this is happening, we will use a show global status like InnoDB log waits. A value of 0 here means the buffer is handling transactions efficiently with no delays. If you see a higher number here like 10, 100 or more, it is a signal that the current buffer size might be too small. If log waits are frequently occurring, it may be time to increase the log buffer size. This adjustment can help accommodate larger or more frequent transactions, which prevents MySQL from having to pause and flush logs so often. Alternatively, you might suggest breaking down large transactions into smaller ones, though this isn't always feasible. To adjust the buffer size, you'd add or modify the InnoDB log buffer size setting in your MySQL configuration file, typically located in the /etc/mycnf. To adjust the buffer size, we would add or modify the InnoDB log buffer size setting in our MySQL configuration file, typically located in the /etc/mycnf directory of our machine. So we would just go to cd/etc. We can do ls and we can find mycnf right here. Sudo vim my.cnf. Here, that's where we did the buffer pool size earlier. So hit I to enter insert mode. Add the new line. InnoDB underscore log underscore buffer size is equal to and that would be all. Escape shift colon, insert, get rid of that. Escape shift colon, right quit. And now we just gotta restart. Our MySQL d.service and start it. And let's go to MySQL and take a quick look at our InnoDB log buffer size once more. So if we look at the InnoDB log buffer size, we see it is now equal to the new value we configured. The InnoDB log buffer size is essential for handling transactions smoothly. Keeping an eye on log waits can indicate whether an increase is necessary, helping ensure that the MySQL server performs optimally. That is all for this session. In the next lesson, we'll take a closer look at the InnoDB redo log files and how they work in conjunction with buffer settings. Thank you for watching, and I'll see you in the next part. Today, let's focus on a couple of key configurations in the InnoDB storage engine, particularly the buffer pool and the flush method. These are crucial to optimize as they help us minimize heavy disk I/O activity, which can slow down performance. First, let's talk about the buffer pool. The buffer pool is part of InnoDB's in-memory structure and it's responsible for caching table data. When data is cached in the buffer pool, it's readily available for queries and doesn't have to be repeatedly pulled from the disk. This is important because reading from memory is much faster than reading from the hard drive. To maximize this caching, it's recommended to allocate at least 50% and ideally up to 75% of your system memory to the buffer pool. This way, the larger the buffer pool, the more data it can store, boosting database speed. Now, the flush method is the next key setting we can adjust. Eventually, the data in memory needs to be written to disk, making changes permanent. The way we manage this memory to disk transfer can greatly impact performance. On Unix and some Linux systems, InnoDB often relies on a system function called fsync to handle this flushing. However, in some cases, especially if you're noticing slowdowns in insert, update, or delete operations, fsync may be contributing to the issue. In our next lesson, we'll dive into the default flush method. Thank you for watching, and I will see you in the next part. Let's go over InnoDB's flush methods. Flush methods control how modified data in memory, called dirty pages, is written from the buffer pool to permanent storage on disk. This process is essential for keeping our data consistent between memory and disk, and InnoDB manages it in the background. The system variable InnoDB flush method lets us set the flush method. By default, InnoDB uses the fsync method. This method flushes data files, metadata, and log files but requires double buffering, which can impact performance due to additional memory and disk operations. Another option is ODsync. This method flushes only the data files, but it too uses double buffering. For improved performance, there is the ODirect, a commonly recommended method. It writes directly to disk without double buffering, avoiding the overhead of the fsync calls. Finally, there's the ODirect no fsync. This method skips the fsync process so it can speed things up further in write-intensive applications, but isn't ideal for all systems, especially XFS file systems. So what's the best method? Generally, ODirect and ODirect no fsync are recommended, but it's wise to test each in your environment to see which works best. As an assignment, you'll check your current flush method, likely set to the default fsync, and then change it to ODirect. You can use the InnoDB flush method system variable to configure this and apply it in the InnoDB settings file we've previously worked with. Let's dive into the demo and see how you can make these changes. Thank you for watching, and I'll see you in the next part. In this lesson, I want to walk you through the process of changing the InnoDB flush method. Let's check the current flush method being used by the InnoDB storage engine. To do this, we'll use the following command: Mysql d verbose and then help grep-i flush, looking for the flush keyword. So as we can see, the InnoDB flush method is set to fsync, which is the default method for flushing data in InnoDB. We can also see that we can change it with this variable name. InnoDB flush method is equal to name of the flush method we would like to use to flush the data. So we got the current configuration. Now let's change the flush method to something else. Specifically, we will change it to ODirect to improve the performance under certain conditions. To do that, we need to modify the MySQL configuration file. We will use the Vim text editor to open the configuration file, which is located in /etc, and then the name of the file is my.cnf. And here, click I to enter insert mode. And as it mentioned in the thing, when we did that mysql d verbose command, we just got to add that variable and set it to we got to add that variable and set it to the method that we look to use. So we're adding the following line. As I mentioned in the documentation, InnodB flush method is equal to oDirect. We can add this comment here as well to indicate that we're setting it to oDirect to improve the performance. Once we're done making our changes, we just hit the escape, shift colon, right quit, and we just got to restart the MySQL service to apply our changes. Let's start back up the MySQL service. Finally, to confirm the flush method has been successfully changed, we can run the same command as before. And we can see the new flush method is oDirect. And that's it. We've successfully changed the InnodB flush method. Thank you for watching, and I'll see you in the next part. Now that we've covered the in-memory structure and InnodB's flushing mechanism, let's dive into the on-disk structure, specifically the double write buffer. Before MySQL 8.0.20, this buffer was part of the InnodB system tablespace IBData1. However, in MySQL 8.0.20 and newer versions, this buffer is now stored in separate files dedicated solely to the double write function. These files provide a critical safeguard for your data. The double write buffer is where InnodB temporarily stores pages from the buffer pool before writing them to their final location in the data files. This extra step allows InnodB to recover pages in the event of a system crash or unexpected process termination during a page write. Without the double write buffer, there would be a risk of losing data if a write operation were interrupted. Although data is written twice, the process does not result in significant I/O overhead. The reason for the double write is to protect against data corruption during recovery, ensuring that a consistent copy of the page is available. Historically, the double write buffer was part of the system tablespace, but as of MySQL 8.0.20, it resides in separate double write files. These files have the extension .dblwr and follow a naming convention like as shown in the slide with IB_1638 0.dblwr, where 16384 refers to the default InnodB page size of 16 kilobytes. There are a couple system variables that control the double write buffer. First is the InnodB double write variable. This determines whether the double write buffer is enabled. By default, this is enabled to ensure data integrity. Then there is the InnodB double write _dir. This specifies the location of the double write files. By default, these files are stored alongside your data files, but it's recommended to place them on the fastest storage available for better performance. While this mechanism greatly enhances data integrity, there are situations where you might want to disable it. If you are more concerned about performance than data safety, you can disable the double write buffer. However, keep in mind that doing so sacrifices the crash recovery benefits. As a part of today's lesson, we'll look at two situations we may encounter. The first is disabling the double write buffer. So if we want to prioritize performance over data integrity, we can disable the double write buffer. Then there is enabling the double write buffer. So here we would configure the system to use the double write files stored in a specific directory. To disable the double write buffer, we will use the skip command, with the appropriate system variable. To enable it, we will specify the directory for the double write files using the Innodb _double_write_dir. This hands-on exercise is designed to help you understand how to work with the double write buffer in a real-world scenario, as these tasks are part of the day-to-day responsibilities of a DBA. Thank you for watching, and I'll see you in the next part. Let's go over the steps to disable, enable, and change the location of the Innodb double write buffer files. Let's dive into how to manage the Innodb double write buffer in MySQL, starting with checking if it's enabled. First, let's log into MySQL and with the MySQL command, and then check the current settings of the Innodb double write buffer with this command. Show global variables like Innodb double write. We can see here that the following output, which shows the default values of the double write buffer. The Innodb double write is set to on, which means the double write buffer is currently active. The Innodb double write files indicates the number of files used, and the Innodb double write pages shows the number of pages used per thread. Now let's disable the double write buffer to optimize performance, if this is suitable for our system. Let's exit. Then we can use the MySQL D verbose help and grep for the double write words amongst the documentation to see how we can go ahead and disable it. We see here we disable with the skip Innodb double write, so we need to add that to our configuration file right here. So if we just go into our configuration and add that line, we will simply be able to disable it. So enter insert mode with I, then skip Innodb double write. Now escape, shift : write quit. Now we just gotta stop and start the service once more real quick. So sudo systemctl stop mysql d, and if we now start mysql d, and we can easily just take a look at the variable again. Oh, I gotta take a look at that variable again, and it is off. And 0 files, 0 pages, so it is off, completely off. Now let's take a look at changing the location of the double write files. If you want to move the double write files to a different location, we can follow the following steps. So first, let's take a look at where the files are currently located. First, let's check where the files are currently stored. So I'm going to ls into this directory, and we can see these two files. These are the double write files right here, IB 1638.4 referring to the size, and that's the first one, and that's the second one. We can check the current double write directory setting using this command once more to get the documentation. So we can currently see the Innodb double write directory has no default value. Let's go ahead and set that. So we're going to make a new directory. Let's make a new directory called double write. So you might need to make this MySQL directory before you do that, but let's go ahead and make this. Oh wait, first I need to make this, then I can make this. So our plan is we have this new directory double write, and our plan is next time we're going to configure MySQL so that these two files get now made here the next time we enable the double write feature. So you got the lib and the log, so I put this double write in the log. Let's go ahead and change the owner of our new directory to MySQL so that it can have all the privileges in order to write and read from it. So we use the change owner command for the MySQL user on this directory. Now let's open up our configuration file. So sudo vim into our configuration file and just re-enable the double write feature and point it to our new directory. So hit I and specify our new path. So Innodb dash double, specify the double write directory is equal to the new folder we made. Hit escape, shift : write quit. Now let's restart the MySQL service and stop and start. Now let's look at the new location of the double write where we made the double write directory, and we can see the brand new files. We can do the command we did previously to see how our double write directory is configured, and it's configured just as we put it in our configuration file. And we can check the global variables with the double write word keyword, and we can see once again it is now enabled to at the directory 4 pages. So in this demo, we verified the current configuration of the Innodb double write buffer, disabled the double write buffer by editing the MySQL configuration file, and changed the location of the double write files to a custom directory and verified the new setup. And this concludes the demo. Thank you for watching, and I will see you in the next part. In this lesson, we'll explore an important Innodb setting, the Innodb flush log at trx commit. This system variable plays a crucial role in managing data integrity and system performance, particularly concerning input-output operations. I believe it is essential to understand this variable because of its impact on both transaction reliability and performance. Here's the concept in simple terms. When the Innodb processes transactions, it manages how data moves from memory to disk. This variable gives us control over how strictly we enforce ACID compliance, ensuring no data is lost, compared to allowing slightly less strict settings for better performance. However, there are 3 modes to choose from, each offering different levels of data protection and performance. First is the default mode. This mode provides full ACID compliance, meaning each transaction is saved and flushed to disk immediately after it's committed. This way, no data is lost, but keep in mind each transaction incurs a disk write, which can slow things down if there are a lot of transactions happening simultaneously. The value of 0 for this variable shows that in this mode, logs are written to disk only once per second, with no immediate action taken at each transaction commit. This provides a performance boost, but any data from transactions not yet flushed could be lost if there is an unexpected shutdown or crash. Then when there is a value of 2 for this variable, the logs are written after each transaction but flushed to disk only once per second. This option still carries a small risk of losing up to 1 second's worth of transactions, but offers a compromise between performance and reliability. So which one should we choose? If data integrity is the top priority and we can't risk losing even a single transaction, we would have to go with 1, as it is the safest option. But remember, this setting could slow down transaction-heavy environments, especially if your hardware has limited resources. 0 can be a great option if performance is a bigger priority than losing a second's worth of transactions. You'll see better speeds, but you should be okay with a potential data loss in the case of a system crash. Then 2 provides a balance of the two, some performance gain while limiting data loss risk. To sum it up, your choice will depend on your specific needs. For environments where any data loss is unacceptable, we would stick with the default setting of 1. But if we're aiming for a middle ground in a high performance environment, 2 might be the best choice. In this lesson, we'll look at how to adjust the Innodb flush log at TRX commit parameter, which controls how Innodb handles log flushing for transactions. We'll go into Mysql. First, let's verify the current value of the Innodb flush log at TRX commit variable. So we're going to look for the global variables like Innodb flush. Take a look at that, and we can find this variable Innodb flush log at TRX commit, and it currently has a value of 1. We'll go ahead and exit. Next, we'll use the Mysql dverbose and look at the documentation where it has the word TRX. We can see that in order to configure the value of the Innodb of this whole value, this is the variable that holds it, and we can adjust that in our configuration file by changing this either to 0, 1, or 2. Let's go ahead in our configuration file. And we'll just hit I and make the simple change of just putting Innodb underscore flush log at TRX underscore commit equal to 2. While we're at it, I'll also put this comment setting for flushing logs in respect to transactions. So hit escape, shift : right quit, and let's restart our MySQL instance. Restart it again. Go into MySQL and go ahead and we'll again look at the variable with the Innodb flush, and now it has the value of 2, and that's it. We've successfully updated the transaction log flushing behavior. Thank you for watching, and see you in the next lesson. We've discussed the basics of Innodb's memory structure as well as the flush mechanisms, double write buffers, and more. In this lesson, let's dive into Innodb's redo log files, which are key for data recovery in Innodb. As you know, Innodb uses a memory buffer to improve read and write speeds, with the data changes first recorded in memory. These updates are only written to disk afterward. If a crash happens before data is fully written to disk, any uncommitted data will be lost. To handle this, Innodb maintains redo logs to ensure data consistency and durability. You might be asking, why do redo logs matter? Whenever data is modified, the change is first recorded in a redo log before being written to disk. This process is known as write-ahead logging. which ensures that we have a record of the modification even if the actual data hasn't been saved yet. If a crash causes memory loss, Innodb can use the redo logs upon restart to restore data to its last consistent state. This recovery process ensures that the database can quickly resume for pre-crash condition. Let's take a closer look at the structure and purpose of the redo log files. The Innodb redo logs are primarily for recovery purposes. They are disk-based, meaning they don't use memory until needed during a crash or unexpected shutdown. These logs store uncommitted changes. Anything left active in memory when MySQL exits unexpectedly is considered an incomplete transaction. Physically, these logs are stored as files on disk. In the ib_log file 0 and ib log file 1 files. By default, the file size is managed by the Innodb log file size variable. The number of log files is set by the Innodb log files in group variable, and the default is 2 files. The log file location defaults to the data directory and is controlled by the Innodb log group home directory variable. Another essential setting is the Innodb fast shutdown with 2 primary options. 0, which represents a value of a clean shutdown. What this means is all data is flushed from memory to disk before MySQL shuts down. It's slower to shut down but faster to restart, as no redo logs are read on startup. A value of 1, which represents a fast shutdown. MySQL will shut down quickly without additional flushing, meaning redo logs will be read on startup to restore uncommitted changes. So the question is, which setting should we use? If data consistency is crucial, a clean shutdown is ideal. It ensures all changes are written to disk and that no recovery is needed on startup. For quicker shutdowns, fast shutdown or a value of 1 is faster, but it requires MySQL to read redo logs on the next startup to restore uncommitted data. Data consistency is crucial. A clean shutdown or a value of 0 is ideal. It ensures all changes are written to disk and that no recovery is needed on startup. For our next hands-on assignment, we'll perform a clean shutdown by setting the Innodb fast shutdown to 0, and afterward we'll delete the redo log files. When we restart MySQL, these logs should be recreated automatically. We'll also check if everything works smoothly by testing data recovery from the recreated redo log files. This way we can see how Innodb handles shutdowns and recovers data when redo logs are required. Thank you for watching, and I'll see you in the next part. In this demo, we will explore the behavior of the Innodb redo log files when the Innodb fast shutdown variable is set to 0. Normally, Innodb uses a fast shutdown process that keeps the redo logs intact, but when we change the value to 0, MySQL performs a more thorough shutdown, and during this process, all Innodb data files, including the redo log files, are flushed to disk. Let's take a look at the current value of this variable. It's 1. And this allows for the fast shutdown. So we're going to change this to 0 to force MySQL to perform a full flush of all the data log files. We set it to 0. Let's double check that it's set to 0. There it is. Now we can exit. And let's go ahead and stop the MySQL service. Now we will check the contents of the redo log directory before deleting the files to ensure that it contains the data. So This is where the redo log files will be kept. And as you can see, there are plenty. Let's just delete the whole folder. Now let's try and look again. It does not exist. Let's make a new folder right here. And we have to make sure we change the owner of that folder to the MySQL user so that they can update, insert, and delete on that folder. Let's just verify that the directory got created correctly. So the directory was empty, but our folder is right there. Now let's finish off by restarting the MySQL service. And it was able to successfully restart. And finally, let's take a look at this folder, and it has all the log files and they all got recreated. So by setting the Innodb fast shutdown to 0, we force MySQL to perform a full shutdown and flush all the data, including the redo log files, to disk. After removing and recreating the log directory, MySQL automatically recreated the redo log files when the service was restarted. And this process ensures that the redo log files are properly handled during a full shutdown. Thank you for watching, and I'll see you in the next part. In this lesson, we'll dive into the concept of the system tablespace in MySQL, which is a crucial element of the Innodb storage engine. To provide some context, we've already covered memory storage. And now we're working our way through the core storage mechanisms. In the upcoming lessons, we will also discuss undo tablespaces. But for now, let's focus on the system tablespace. The system tablespace is the primary location where the change buffer is stored. It also contains table data and index data, but this depends on whether the tables were specifically created within it. Ideally, however, tables and indexes should be stored in file per table or general table spaces for better performance and organization. Older versions of MySQL use the system tablespace for more than just data storage. For example, the Innodb data dictionary, which contains metadata about the tables, was stored in the system tablespace in those versions. Additionally, the system tablespace once housed the double write buffer, which is a mechanism used to improve data integrity. In MySQL 8 and later, the approach has shifted, and tables are generally created outside the system tablespace to keep things organized. The default name for the system tablespace data file is ibdata1, and it is typically created in the data directory by default. However, the system tablespace is flexible. It can contain multiple data files. The size and number of these data files are controlled by the Innodb data file path system variable. This variable specifies the file name, size, and whether it should be auto-extended if necessary. The system tablespace is very important because it stores essential information about the structure and the operation of your MySQL database. This includes metadata for all Innodb tables, so it is crucial for MySQL to function properly. When working with the system tablespace, keep in mind that taking backups is highly recommended. If something goes wrong and you need to recover the system tablespace, it can be a complicated process. In some cases, you may even need to drop and recreate the databases, which can be time-consuming, especially with large data sets. In this exercise, we'll add another data file to the system tablespace. This new file will be set to a size of 10 MB and configured to auto extend. We will also move the data file to a new location for better organization. After making these changes, we'll restart MySQL and verify that everything works as expected. This is an excellent opportunity to practice managing the system tablespace. Keep in mind, whenever you are making changes to the system tablespace, always take a full backup beforehand. Dealing with system tablespace corruption or recovery is not easy. If the system tablespace becomes damaged, recovering the data might require performing logical backups, and if you're working with large amounts of data, this could take days. Thank you for watching, and I'll see you in the next part. In this demo, we'll go through the process of moving the Innodb system tablespace data file to a new location and reconfiguring MySQL to recognize this new location. This is useful in cases where you need to manage disk space more effectively or isolate the system tablespace. We'll also adjust the configuration file to reflect the new file path and make sure everything is running smoothly. We'll start by checking the current value of the Innodb fast shutdown variable. This determines how Innodb handles flushing when the server is shut down. To ensure a clean shutdown, we set the Innodb fast shutdown variable to 0. With the set global Innodb fast shutdown equals 0, this forces Innodb to flush all data pages before shutting down. Next, let's stop the MySQL service to prepare for the file system changes. We'll create a new directory for storing the system tablespace data file and move the file to this new location. So we'll make Innodb directory. Next, we're moving this ibdata1 data file to the new directory we just made. Let's just check that our new file is in this directory. There it is, ibdata1, the system tablespace data file. Since we made a new directory, we need to change the ownership on it. So let's just quickly do a change owner on this whole folder. That way MySQL has the necessary permissions for the new directory. Next, we need to open the MySQL configuration file and update the Innodb data home directory and data file path to point to the new location of the ibdata1 file. We are saying the ibdata1 file is 12 MB and we're making a second file named ibdata2. That'll be 10 MB and it has the auto extend property, meaning if it can grow all by itself if it needs more space. Let's hit escape, shift colon, escape, shift colon, right quit. Now let's start the MySQL service. Show global variables to see our new variables. As you can see, the data file path got configured as we put in our configuration file, with the first file being 12 MB and the second file being 10 MB with the ability to auto extend. And here's the new path of the home directory. We can look for more information about the ibdata1 file and ibdata2 files. With this command, we can see more information about the ibdata1 and 2 files. Let's go ahead and exit. Let's take a look at that directory. There we can see our two data files and IB temp1. So in this demo, we've successfully moved the Innodb system tablespace data file to a new directory, updated the MySQL configuration to reflect this change, and confirmed that the new configuration was applied successfully. So this process allows us to better manage the Innodb data files, especially when dealing with disk space limitations. Thank you for watching, and I will see you in the next part. Today we'll be exploring the purpose and role of undo tablespaces. As the name suggests, undo tablespaces play a crucial part in undoing certain actions within a database, specifically related to managing ongoing transactions. Much like the redo log files we previously discussed, which are used to reapply or recover changes, undo tablespaces serve a distinct function by storing undo logs. These logs are collections of records that detail how to revert the most recent change made by a transaction to a clustered index record. Essentially, undo logs capture an image of the data as it was before any changes. This way, if a transaction is rolled back rather than committed, the database can easily restore the previous state of the data using these stored logs. By default, when a MySQL instance is initialized, two undo tablespaces are created automatically. It's important to note that a minimum of 2 undo tablespaces is required in MySQL, and each undo tablespace must contain at least one data file. The default names for these 2 undo tablespaces are Innodb undo 1 and Innodb undo 2. Additionally, the system variable Innodb undo directory specifies the location of these undo tablespace files, defaulting to the data directory if no other location is provided. In the next exercise, we will move these undo tablespaces to a specific directory within Innodb, ensuring each undo tablespace has its own designated data file. Thank you for watching, and I'll see you in the next part. Today I'll be walking you through the process of moving the undo tablespace files in MySQL. We'll go step by step to make sure the changes are effective and that everything is working smoothly. Let's start by checking the current settings for the Innodb undo directory and the number of undo tablespaces. We'll go into MySQL, and we could see show global variables like Innodb undo and then the wildcard. I'll also check the Innodb fast shutdown after this to make sure that we can perform a clean shutdown later. Let's run this. We could see the Innodb undo directory is just set to the default. We have 2 undo tablespaces as we can see with this number. Next, let's check the Innodb fast shutdown setting. The fast shutdown is set to true. To ensure a clean shutdown, let's set that to 0. We'll use set global Innodb fast shutdown equals 0. Next, let's exit and shut down the MySQL instance. With MySQL stop, let's locate the current undo tablespace files. We'll go into the var lib and MySQL directory. We could see our 2 undo tablespace files, undo 1 and undo 2 right here. Let's go ahead and move these to a new directory. I'll move undo 1 to my Innodb directory where I hold my moved files. I'll move the first one, and I'll move the second one. Next, let's make sure the ownership of these files is set to MySQL. So we'll use the change owner command and allow MySQL privileges on this directory. We'll update next. Now we need to tell MySQL where to find these files. So let's edit the configuration file to set the new path for the Innodb undo directory. So we'll go and modify our my.cnf file. We'll go down here, hit I to insert, configure Innodb tablespace. Let's go ahead. So we'll set the Innodb undo directory will be equal to the new directory where we moved the files. Shift colon right quit. Escape shift colon right quit. And next, let's start up our MySQL instance. If we did everything correct, it'll start up correctly. Let's enter MySQL. And now let's check out the new directory. So that's the new directory that we configured for our undo files, just as we worked just fine. Let's go ahead and let's check the undo tablespace in action with a quick transaction demo. Let's check the current state of the Innodb engine. So we can use the show engine status command. And we can see if we go to transactions that currently there are 0. Let's go ahead and start a transaction. We'll use the world start transaction and update country set. We'll do this update statement where we'll just set the names of all the countries to a blank space. Show tables. Oh, continents. Okay. Okay, so we have these 7 continents. We'll just update continents instead of country. And set CNAME equal to this. So we see 7 changed rows. Now let's go ahead and show table, show engine status for Innodb. And if we go to transaction, we can see the undo log entry has 7 entries, the same amount of rows that we have changed. So if we commit, it'll write the changes permanently. But for this demo, let's roll it back. And our changes are now in the undo logs. That's the point I want to show. So if we roll back and we take a look, it'll go, the undo logs will be emptied. And that's it. We've successfully moved the undo tablespace files, configured MySQL to recognize their new location, and observed how undo logs work in a transaction. Thank you for watching. Please subscribe, and I'll see you in the next part. Let's take a closer look at temporary table spaces. MySQL provides 2 main types: session temporary table spaces and global temporary table spaces. Each plays a unique role in managing temporary tables. The session temporary table space handles all user-created temporary tables. These are only available within a session, and they are removed automatically when the session closes. On the other hand, the global temporary table space is used for tracking rollback segments for any changes made to user-created temporary tables. Only one data file is used for global temporary table spaces called ibtemp1. By default, this file is 12 MB and resides in the Innodb data home directory. The Innodb temp data file's path parameter specifies the location, size, and auto extension settings of the IB-temp1 file. For those curious to explore, you can check the location and size of these files using the commands like show global variables, like Innodb temp data files path. This will give you more insight into where the temporary tablespace files are stored, usually in the var lib mysql under IB-temp1. That's it for temporary table spaces. They're mainly for managing temporary tables, so once we understand that, there's not much more to configure here. Thank you for watching, and I'll see you in the next part. Let's discuss the general tablespace and file per table tablespace. First, let's look at the general tablespace. Generally speaking, these are not commonly used, but it is important to understand the concept behind them. In a general tablespace, multiple tables can exist in a single IBD file. For example, you might have a tablespace named tablespace1.ibd, which contains multiple tables. Each tablespace can have several tables, so you might see a tablespace1.ibd file containing several tables with different table names like table 1, table 2, and so on. The key thing to remember about general table spaces is that multiple tables can share a single IBD file. So for instance, if you create a database and then create a table, you might specify a tablespace for that table. The key thing to remember about general table spaces is that multiple tables can share a single IBD file. This is in contrast to using file per table tablespaces, where each table has its own individual IBD file. It is important to note that in general tablespaces, one IBD file can store several tables, and you can use create tablespace to create a new tablespace and drop tablespace to remove it. Now that we've covered general tablespaces, we will move on to discussing file per table tablespaces in the next lesson. In this lesson, let's discuss the file per table tablespace part of the Innodb architecture. File per table means that each table has a dedicated tablespace, and the file extension is .ibd. In simpler terms, every table is a self-contained tablespace. If you have two tables, dt1 and dt2, each has its own .ibd file representing the data storage for each table separately. Managing tables individually is easier with file per table, especially since MySQL 5.7 and up has this option enabled by default. Instead of all data in one large file, tables have dedicated storage, which improves isolation, backup flexibility, and maintenance. To confirm that file per table is enabled, we can run the show global variables like Innodb file per table. Each table with file per table enabled has its own .ibd file. This setup makes tables easier to manage and is recommended for improved organization. To finish off, let's do a quick demonstration to see how file per table tablespace works in action. Let's go to MySQL. First, let's check if Innodb file per table is enabled. This setting ensures that each table has its own .ibd file. We can do show global variables like Innodb file. So as you can see, it is on, which confirms that the setting is active. Next, let's look at the databases and switch to our employees database. So I've switched to the employees database. Next, we can view the current tablespace in the employees database by querying the Innodb tablespaces table. And if we show tables for employees, we can see employees has employees, staff, and test 1. And here we can see that each table has its own IBD file. So these are all the IBD files for the table. So employees has the employees IBD, the staff, and test 1. Let's go ahead and make another table. We'll call it test 2. Now let's take a look at the information schema InnoDB table spaces. We can see there's a new entry for test 2 confirming that this table has been allocated its own IBD file. Finally, let's go to the MySQL data directory to confirm each table has a separate IBD file. So if we go to MySQL, you can see there's a world folder and employees folder. So if we go inside employees, we can see 4 IBD files: employees, staff, test1, and test2. And that's it. This demonstration shows how file per table makes each table easier to manage by giving its own storage file. This is one of the great benefits of using the file per table tablespace in MySQL. Thank you for watching, and I will see you in the next part. In the last few parts, we covered InnoDB architecture. We talked a lot about various in-memory structures like the buffer pool, change buffer, and log buffer, and how these interact with on-disk structures. We've highlighted that a larger buffer pool can boost performance because frequently accessed data is more readily available in memory. Today, let's discuss an option that MySQL provides called a dedicated MySQL server. This setting allows InnoDB to manage its own memory and flush settings automatically, taking some of the configuration work off your hands. So what exactly is a dedicated MySQL server? If you turn on the InnoDB dedicated server settings, MySQL will handle several configuration tasks on its own, which could simplify management and improve performance. By default, this option is off, but if enabled, MySQL will automatically configure some key settings for you. First is the InnoDB buffer pool. This is crucial as it impacts how much data can be kept in memory. Next is the InnoDB flush method, and this controls how MySQL writes the data to disk, which affects durability and performance. Next is the InnoDB log file size and InnoDB log files in group. For older versions, these help manage the redo log files, and in MySQL 8.0.30 or newer, the InnoDB redo log capacity replaces these, simplifying the setup. In MySQL 8.0.30 or newer, there is the InnoDB redo log capacity, which replaces these, simplifying the setup. The setting name for enabling this mode is InnoDB dedicated server. To enable it, your MySQL instance needs to be on a dedicated server with no other application sharing system resources. If MySQL is running alongside other applications, enabling this feature won't provide the same benefits, so it's best left off those cases. How does MySQL calculate the buffer pool size with this setting enabled? If the server's memory is less than 1 GB, the buffer pool defaults to 128 MB. For memory greater than 1 GB but less than 4, the buffer pool is set to half the system memory. If the server has more than 4 GB of memory, the buffer pool takes up 75% of the total memory. Now let's try this out by enabling the dedicated server mode on our instance, and we'll experiment with different memory settings. Keep in mind though that even if InnoDB dedicated server is on, we can still override specific settings as needed. For example, if we want to allocate a custom buffer pool size. Thank you for watching, and I'll see you in the next part. Let's look at how to enable and test the InnoDB dedicated server feature in MySQL. First, let's check if the InnoDB feature is currently enabled. We'll go to MySQL, and we'll show global variables like InnoDB dedicated. So As you can see, the Innodb dedicated server feature is currently set to off. This feature is useful because it automatically configures settings like the Innodb buffer pool size, flush method, and log file size based on the server's memory. If we enable it, we won't have to manually set these values ourselves. So now let's open the MySQL configuration file and comment out the current manual settings for these options. So we'll exit and we'll go into the my.configuration file, hit I. So we can go ahead and comment this and this, because the dedicated server feature will configure these. Next, let's go to the top and we'll put the dedicated server, and we'll just add that line. Innodb dedicated server is on, so that'll be all. Escape, shift colon, right quit. So now that we've made our changes, let's restart the MySQL server so that they can be made into effect. Turn it on. Let's go into MySQL and we can see, so here we can see the Innodb buffer pool size. Before, this was set to 256 MB because the server has less than 1 GB of memory. Now it has automatically been adjusted to 128 MB. Let's take a look at the flush method setting. Now it is O-direct, no fsync. Before it was just O-direct, which was also due to our limited memory. Finally, let's check the Innodb log file size and log files in group settings. Now we can see that these are set to 50 MB and the log file groups are still 2, also configured now automatically by the MySQL server due to the dedicated server feature. And finally, we can go to the top and check this. And we can now see it is the Innodb dedicated server is set to on. And that's it. We've seen how the Innodb dedicated server feature can simplify configuration in a MySQL environment. Thank you for watching, and I'll see you in the next lesson.